Hey, everybody. So we're going to jump into, in this lecture, we're going to talk about, the big idea is defining the sine and cosine functions. And to use this, we're going to use something called the unit circle. But I first just want to jump back for a minute and recall what functions are. These are objects that we study a lot, right? You study them a lot when you first start pre-calculus. These functions, the trigonometric functions, when you get into calculus, you're looking at functions all the time. But I think we often have a little misunderstanding of what they are, kind of just forget what they are explicitly because we get so used to them being around. So just as a little review, recall what a function is, right? A function will have an input leading to an output, right? It's pretty much that simple. There's some little details. Each input can only have one output, but like that's the basic idea. You give me something, I'll give you something back. And if you give me the same thing, I'll always give you the same thing back, right? So that they don't change, right? Like if you have a different input, you'll get a different output, but the same input will always lead to a certain output. One way we can think about how this output happens is as a set of instructions, right? That's what that arrow is, right? And sometimes the instructions might be excessively simple. For example, this could be a function. I'll call this the function. I'll just call it capital F. And maybe my whole function is the following set of instructions. I take the inputs 1, 2, and 3. So there's only 3 inputs allowed. And the instruction is just telling you exactly what output each one of those has, right? So I could maybe say that the input 1 takes me to -7. The input 2 has the output of itself, and the input 3 has the output of 101, right? I don't have a lot of meaning to this, but it is a function. I've told you my inputs, and for each of those inputs, I've given you an output, right? This is not a typical way we have a function. Functions you're more familiar with might be something like this. G of x is equal to x squared minus 7 divided by 2. This algebraic expression here is the set of instructions I was talking about, right? We could say this in words, something like given an input, square it, subtract 7 from this result, divide the current total by 2, return this result. Right, so obviously algebra is great. We can express this long set of instructions in a more simple way to look at it, but that's really what it's saying. You give me a number, I'm going to square that number, I'm going to subtract 7, I'm going to divide by 2, and I'm going to give you what I get back, right? That's what a function does. Sometimes they're more complicated. I won't go through trying to write this one down in words, but I could have something like x squared times the square root, the natural log of the square root of x squared plus x to the 4th plus 9, all divided by x to the 1/3 power plus 2x or something, whatever it is, right? So there's a whole bunch going on there, but still it's a set of instructions. We don't even need to have our functions necessarily deal with numbers. We won't do this very often, but for instance, a perfectly reasonable function could be the input is what day, what date was it? And the output could be what was the color of the first bird I saw outside the window, right? That would be a function. You tell me what date. If I've been keeping records, I could tell you what was the first bird I saw or the kind of bird I saw, right? So that's what functions are, right? And the reason we're going through all this is because the sine and cosine are functions. Sine and cosine are functions. They're going to have this idea, input leading to an output, and just like these other ones, there's some instructions in here. The instructions here fall into the complicated category, and not just complicated like this h of x I've written here. They're in some way close to that bird instruction, right? It's well, we'll get into it right now, but there's a fairly complicated set of instructions for given an input, finding out what the output is. We won't mostly have to deal with what those instructions are. We do need to understand what they mean, but we won't actually use them to compute the values in most cases. We'll find other ways to compute the values, but this definition is really important to understand. So let's jump into what is the instructions for the sine and cosine functions. We're going to begin with something we call the unit circle. So this is going to be a circle with a radius of 1. Oops. And centered at, we're going to put its center at the origin of some set of axes, right, on a coordinate system. So let's see if I can get it fairly well centered. That looks close. Okay. So there's the beginning. We have, let's just put in one coordinate point. If this was a unit circle, this would be the point 0, 1, right? And let's add now an angle in standard position. So I start with its initial side along the positive x-axis, and its terminal side will be somewhere, right? So I've drawn it here somewhere in the first quadrant, but it could be in any of the quadrants. These instructions don't rely on that. This is just the simplest drawing to make, okay? So now remember, this is a unit circle, so this, we can put in a couple other things. This would be the point 1, 0, right? This radius from the center to the circle has length 1. Okay. And let's give this angle a name. Okay, so the angle from here to here, I'm going to call T. Okay. Well, this this angle hits the unit circle on the x-axis and at one other point. If the angle was 0, which we'll talk about later, then that terminal side would be in the same point. But it, in almost every case, going to hit at some other point. And even if it hits in the same point, whatever point it hits at, whatever point the terminal side hits the circle at, we'll have coordinates that we call x and y, right? And just another one of those things we see all the time, but we might forget exactly what they mean. X is just this horizontal distance. Y is just this vertical distance, right? That's what coordinates tell us, our distance from the origin horizontally and vertically. All right, so we're building these sine and cosine functions. Our instructions are, so far, you have to get a set of coordinates, you have to get a coordinate system, a set of axes, put a unit circle in the middle of it, take an angle and put it in standard position, meaning its vertex is at the center and its initial side is along the horizontal axis. Its opening counterclockwise is our positive direction. And then we look at the place where it intersects that unit circle. Given all that, the cosine of the angle T, let's do it here, cosine of angle T, which we would just write as cos T, is the x-coordinate of the place where it intersects. Right? So given an angle T, we define this function called cosine. Its input is an angle, and the output is the x-coordinate of the place where that angle's terminal side intersects the unit circle when that angle is placed in standard position on that circle, right? So it's a complicated set of instructions. And if you actually wanted to compute these things by hand, you'd have to draw a perfect circle, center it there, represent your angle perfectly, place it in the center, and its initial side on the positive x axis, and then you'd have to figure out exactly where it intersects the circle, measure that x coordinate, and there you go with your cosine. This is obviously a ton of work, and like I said, we won't always be doing that. We'll almost never be doing that. But conceptually, this idea is going to be very important. We will use it all the time. In a similar way, we get the sine of angle t, sin t, and that's going to be the y coordinate. Okay. In other words, this the coordinate point here is the cosine of t, sine of t. Okay. This is the definition of our trig functions. These two trig functions. We'll see in the next section that there are more than these two, but these are the two basic ones that we can build the rest out of. And we have related them to circles instead of perhaps the triangles. You may have seen them first. So let's do a couple of examples with this idea. There's a couple we can do easily. So for example, let's say I wanted to compute the cosine of 0 and the sine of 0. All right. So let's draw ourselves a unit circle. Thankfully, this thing fixes my terrible circles. Maybe I'll center that just a little bit. So hard to tell, but I think that might be about right. Well, 0 is the angle. So an angle of 0 means its terminal side is in exactly the same place. It's intersecting at the point 1, 0. Well, the cosine of the angle is the x coordinate of the intersection point. This intersects at the point 1, 0, so its cosine is 1. The sine of the angle is the y coordinate of the point of intersection of that angle with the unit circle when placed in standard position. In this case is 0. So that one is one we can do fairly simply, actually using the definition. Let's do one more. Let's take something like sine and cosine, I don't know why I switched orders, of 3 pi over 2. Well, let's remember where 3 pi over 2, I'm dealing in radians here. I'm going to always deal in radians. Unless I note otherwise, I would put degrees next to it if this was in degrees, that little tiny circle, or just write the word degrees. So in radians, remember all the way around is 2 pi. So a quarter of the way around is a quarter of 2 pi, or pi over 2. Whoops, I didn't mean that to become a smooth curve. So we get pi over 2, halfway around is pi, 3 pi over 2 is all the way over here. So this is an angle 3/4 of the way around the circle, right? So it's, again, it's a positive angle, so I'm moving in this, it's different even though it's coterminal with, that was our language from last time. The angle going in this direction, but that's not the one I'm talking about now. I'm talking about going all the way around. Well, where is this going to intersect? Again, similar to the one we just did, this is following the negative y-axis, and that must intersect the unit circle at 0. It's on the y-axis, so the x-coordinate is 0, and the y-coordinate is -1, which means the sine of this angle is -1, and the cosine is 0. And let's even do, as long as I mentioned it, negative angles. Well, these are going to be exactly the same. Negative pi over 2 is a different angle, but it's coterminal with the one we just did, meaning it has the same terminal side. So if I go negative pi over 2, that's in the negative direction quarter turn, I end up on the same exact, with the same exact terminal side, right? Just going in the other direction. And so this has the same y coordinate for the sine value and the same x coordinate for the cosine value, okay? So again, we're this complicated set of instructions. We take an angle, put it at the center of the circle, look at where it intersects the unit circle, take the x coordinate, gives you the cosine of that angle, the y coordinate gives you the sine of that angle that you have there. Okay, we're going to do one more example that gets a little more complicated than the two we just did. Well, we're going to do more than one more example, but we're going to do one more right now. So again, draw my unit circle. We'll call that close enough. And let's do the angle. Let's do the cosine pi over 4 and the sine of pi over 4. Okay, so sine of pi over 4, or let's just think about the angle pi over 4. We just saw that going from, well, I'll draw on the terminal or the initial side first. So here's my initial side. We know that going a quarter of the way around the circle is pi over 2. Pi over 4 is half of pi over 2. And so it's an eighth of the way. It splits this quarter circle in half. So it's something like this. So this angle right here is going to be pi over 4. We've got this radius of 1. And we're looking for the x and y coordinates of this intersection point. So we're gonna do a little geometry here to come up with this. I want to notice, remember what I said earlier, if we drop this down here, this distance here is my x coordinate, this distance here is my y coordinate, and this forms a little triangle. So I'm going to redraw that triangle and make it a bit bigger. How about right here? So we've got there's my right angle. This is pi over 4. This length is 1. This is x, and this is y. So a little trick to this one, this right angle is the same angle as that quarter turn of a circle. This will be pi over 2. If you recall from geometry, if you sum the angles in a triangle, you'll always get 180 degrees. It's probably how you've heard it. That is a straight line angle. In terms of radians, that's pi. So that means pi over 4 plus pi over 2 plus whatever this angle here is have to sum up to pi, which means this must be a quarter, right? We've got a quarter pi, half pi. We need another quarter of pi to get a total sum of pi. The fact that these two angles are the same means that these two sides are the same, right? In this drawing, x and y must be the same. Okay, it's an isosceles triangle. So here, this is some pretty important information for us. We're going to use one more fact from geometry. The Pythagorean Theorem tells me that when I have a right triangle, right, I've got an angle of pi over 2, if I take the sum of the squares of the two legs, in this case, that's x squared plus y squared, they're going to equal the square of the hypotenuse, which in this case is 1. 1 squared is still 1. But since x is equal to y, this is just x squared plus x squared, or 2x squared is equal to 1. X squared is equal to 1/2. So that x is going to be 1 over the square root of 2. Well, it's technically plus or minus, but I can see in my picture that we're in the positive. We have a positive x direction, so this is going to be positive. And then typically people write this in a different form. They multiply by 1 to get root 2 over 2. I don't find it that important, but it is how you'll often see it written. So I'm going to go ahead and write it that way, which means y is equal to root 2 over 2. This gives me my coordinates. The coordinate points right here have got to be root 2 over 2, root 2 over 2. And that means cosine of pi over 4 is root 2 over 2. And sine of pi over 4 is also root 2 over 2. Okay, so that's our definition. I'm gonna say it one more time. When we have to find the cosine and sine, let's just do one at a time. To find the cosine of an angle, you start with a unit circle centered at the origin of an xy plane. You place the angle you're interested in finding the cosine of at this and in standard position. That means its vertex at the center, its initial side along the positive x-axis. The cosine of that angle will be the x-coordinate of the point where its terminal side intersects the unit circle. The sine of the same angle will be the y-coordinate of the point where it intersects the unit circle. Okay. So we did a few examples of how to compute, but we used we picked some very particular angles. I picked ones that lined up with the axes, or this one that kind of split in half. So there was some pretty easy geometry to get there. This isn't always possible, and there are much more sophisticated methods for computing some of these values that we won't have to deal with right now. But what we will have to know is precisely what this definition means, or what this definition is, so that when we see cosine of an angle means a number, we don't forget that that means, oh, if I put that angle in a unit circle, that's the x-coordinate where the angle would intersect that unit circle. Another thing I want to point out is, if you have heard of sine and cosine in the past in terms of triangles, this new definition gives us something really important that the triangle definition does not, which is that we can now use sine and cosine for angles that were never possible with triangles, right? If you're dealing with a right triangle and you are looking at the angles that are not the right angles, which is how you define these trig functions with triangles, those angles have to be between 0 and pi over 2, because as soon as, if I have a right angle and I'm trying to draw a right triangle, if I try to make this other angle pi over 2, 90 or more, there's no triangle here, right? This one's already a right angle. If I make this one also going straight up, there's no triangle. Or even worse, if I make it bigger than 90, there's not going to be an intersection point. And so there's no way to make sense of those definitions for trig that have to do with right triangles. However, in this definition, for instance, I can take the angle, let's take this angle that goes around several times and stops right here. So this, let's call this angle, how many times did I go around? I went all the way around once, and then 1.5 times, and then another 1/8 of a time. So let's call this is 2 pi plus pi plus pi over 4. So 13/4 pi. Okay, that's what this angle is, 13/4 pi, right? It's impossible to think about a right triangle with this angle. It just doesn't exist. However, with this definition, this makes perfect sense to talk about the sine and cosine of this. We just need to know the x and y coordinates. And in fact, we can use the work we just did to figure out what they are. Notice the reference angle, if you remember that from the previous video, one of the previous videos, this small angle between the terminal side and the x-axis, we're ignoring all these extra rotations. this is going to be an angle of pi over 4, right? With the 13/4 pi, this is going to be, I could write this as 8/4 pi plus 4/4 pi plus 1/4 pi. This is 2 pi going all the way around once. This is just pi going around another half turn, so that's around once and a half. Then this last little bit is just this 1/4 of pi. Means that the shape in here is exactly like the shape we just did. In other words, I can draw that green triangle I had over there, I could fit it in right over here. And even though I've moved it around, it's going to have all the same geometry of the triangle that we had when we had it in the first quadrant, which means the distances are the same, they're just in a different direction. And so this coordinate point where we intersect is going to be negative √2/2, right? Instead of being in the positive, right? That little triangle, if I fit it over here, would go right there. Positive √2/2, √2/2. We're moving the same distance, but in the negative x direction and negative y direction. And so we get this, okay? And so now our cosine of 13/4 pi is negative √2/2, as is the sine of 13/4 pi, negative √2/2, okay? This is a pretty big deal that we can expand the kinds of angles we can put into these sines and cosines functions that we couldn't do when we just had a definition based on triangles. We will see that definition and how it relates to this. It's not wrong, it's just limited. With this definition, this is the last idea for this video, we get a very, very impact for these functions. The domain for sine and cosine, remember that is all the input values that are available, right? What kinds of numbers can I put in? What kinds of angles can I put in? The domain for sine and cosine is all real numbers. That's what this symbol means. All real numbers, right? Or if we want to do it in interval notation, negative infinity to infinity, right? You can put in absolutely any value. Negative values work. We can spin this direction as many times as we need to, and for every value, it represents some amount of turns around this thing, and our angle will stop somewhere and we'll have an intersection point, okay? What about the range? Well, remember, the range is the output. What's the largest to the smallest values, or the smallest to the largest values that these functions can output? Let's think about one at a time. Looking at this unit circle, the cosine function, the x values are the largest over here and the smallest over here, and they'll hit every value in between, right? So this is the point -1, 0. This is the point 1, 0. And those x values are all I care about. Any x value between -1 and 1 corresponds to some point on this circle, right? Whether it's along the top or the bottom, right? Pick 1/2, somewhere in here, there's an intersection with 1/2. And so its range is -1 to 1 inclusive, meaning including that they can actually achieve the values -1 and 1. We could write this as an interval, -1. We'll do it for cosine. Cosine is always between -1 and 1. And exactly the same thing holds for sine. We're just looking at the vertical values. We see that here, the y value goes as high as 1, and here it goes as low as -1, and it hits every value in between as we move around this circle. And so those are pretty big characteristics of these functions. Their domains are everything. Any number is appropriate. Any real number is appropriate to put into these functions. The ranges will always be between -1 and 1. So if you're ever doing some work and you come up with a value for cosine or sine, the output value, and it's bigger than 1, you've made a mistake. They have to be between -1 and 1. Okay, that'll do it for this one. I'll see you in the next one. Thanks, everybody.